Today we are going to see the PV diagram. The PV diagram. Here we know the equation, that is, we consider the equation W equal to integration Vi to Vf dW, which is equal to integration Vi to Vf P dV. This integral represents the work done in changing the volume of gas. The area under PV curve also represents work done in this process. Suppose we consider a PV curve. We consider here 3 PV curves. We will see one by one. Here, suppose we consider pressure on y-axis, volume on x-axis, pressure on y-axis, volume on x-axis, pressure on y-axis, volume on x-axis. Suppose this is figure A, this is figure B, and this is figure C. Now, here we consider, suppose state changes from 1 to 2. Suppose we consider this is the PV curve. Here, this is 1, this is 2. Now, here, suppose this is the, we consider P1, we consider this pressure, P2, we consider this volume V1, this volume V2. Suppose from 1 to 2. Now we consider reverse case. Suppose this is the PV curve. Here we consider this is 1 and this is 2 in this direction. Suppose this pressure is P2, this pressure is P1, this volume is V2, and this volume is V1. And we consider another type, suppose 1 to 2. Suppose here this is 1 and this is 2. Here P be the pressure, and here we consider V1 be the volume and V2 be the volume, 1 to 2. Now here we consider this area under the curve, all this area under the curve. Again here area under the curve, and here also area under this straight line, this total area. Then what is the difference in these three? Here you see, here 1 to 2, state changes from 1 to 2, that is P1 to P2 pressure changes, and V1 to V2 volume changes. Here volume increases and pressure decreases. That means here we consider there is a expansion of that gas, and here the work is positive. Work is positive. There is expansion of gas and work is positive. In second case, in figure B, here state changes from 1 to 2, that means pressure changes from P1 to P2, volume changes from V1 to V2, but here pressure increases and here volume decreases. That means here is a compression of gas, and here work done by the gas is negative. Now here what happens? Here you see state changes from 1 to 2 at constant pressure and volume increases V1 to V2. Here pressure is constant, and so here we consider expansion at constant pressure, and here work is positive. This is all about the PV diagram. That means we consider that is expansion, compression, that means when changing pressure, volume changes, changing pressure, volume changes, and these two curves are isothermal curves. Here temperature remains constant, and here we consider that is at constant pressure volume changes. Expansion at constant pressure and work is positive. Here also work is positive, here work is negative. This is all about the PV diagrams. Now we will consider next article, thermodynamic process. Thermodynamic process. A thermodynamic process is a process by which the initial state of the system changes to the final state. Means initial state to final state. This change is called as this process is called as thermodynamic process, and process in which the state variables of a system, here state variables of the system occurs infinitesimally slowly, and this is called as quasi-static systems. These are called as quasi-static systems. Now we consider here in this thermodynamic process, we consider two articles. In that, first is work done during a thermodynamic process. Work done during a thermodynamic process. This is our first article. And second, we consider that is heat added during the thermodynamic process. Work done and heat added during the thermodynamic process. We consider first. Here we consider, suppose this is the PV diagram. Suppose we consider this is the PV diagram. Suppose state A having volume Vi, pressure Pi, and we consider state B having volume Vf, pressure Pf. State B, we'll write here state B. Now here we consider there is a change of state from A to B. So I will write here, this is Pi, we consider this is pressure Pf, here is pressure on y-axis, volume on x-axis. Similarly, suppose this is Vi is the initial volume, Vf is the final volume, and suppose state changes like this from A to B. This is the first way. Now we consider second like this. See here, this is the second way. A to C and C to B. This is the second way. And third way we consider here A to, suppose I write here D, A to D and D to B. That means we consider here three ways. That is, state changes from A to B by one way on this graph. Now second way is A to C and C to B, and third way is A to D and D to B. Now here state starts from A and state reaches to B. Here suppose we consider this first path. Suppose I will write here pressure, volume. Suppose we consider this is the first path, A to B, first path. Then here suppose I consider here Pi is the pressure, Pf is the pressure final, Vi is the initial volume, Vf is the final volume. Now state changes from by this way 1 from A to B like this, then work done in this process is shown by the area under this curve. This is the work done. See here. This is the work done. Suppose I consider this is the figure B. This is figure A. 3 ways are there. In figure B, only one way. Now this is the work done. Now we consider third figure. Suppose this is the figure C. Pressure is here, volume is here, and state changes from A to B. A to B by this way. Here. That is from A to C. This is C, and C to B. Here we can suppose PI is the pressure. This VF is the pressure. VI is the volume. VF is the volume. Then in this case, A to C, C to B. That means at constant pressure PI, volume changes from VI to VF. And whenever it reaches at C, then at constant volume VF, pressure changes from PI to PF. And in this case, work done is given by this. That is area under this line. Total area under this line. Now we consider suppose third way. Same figure we consider. Pressure is here. Volume is here. Now A to B. This A. Suppose PI is the pressure. B. PF is the pressure. VI is the volume. VF is the volume. Now state changes like this from A to D and from D to B. Now what happens here? You see, at constant volume VI, pressure changes from PI to PF, and after that at constant pressure, volume changes from VI to VF, and in this case, work done is given by this shaded region. Now, if suppose this is diagram D. Now, if we observe these diagrams B, C and D, then in all these three diagrams, work done is not equal. See here, this shaded region, this area is, suppose any area, then from this area is greater, and from, if we compare these two, this area is little smaller. That means work done are different. That means we can say that here work done in these three ways, they are different. That means work done does not depend on initial and final states, but it depends on path which that system traces. That means here we just 1, 2, 3. These are the three paths. Then here that system traces different paths, and so therefore work done during a thermodynamic process is not same. It depends on the path traced by that system. This is the important point. That is, work done by the system depends on path traced by the system. This work done, that means whether these initial and final states are same, but work done are different. This is our main idea. So I hope you all understand this. Work done during a thermodynamic process, it depends on path traced by the system. Now we consider next article. Second article in this, that is heat added during the thermodynamic process. Heat added during the thermodynamic process. Suppose here we consider, again we consider here two ways. Here you see, suppose this is the chamber. In this chamber, suppose we consider we place a gas. Suppose I consider another one. Suppose here we consider state 1 and this is state 2. Suppose we consider here this is the piston. This is the piston. Now suppose Vi, this is the initial volume. Now we consider, suppose we heat the gas. We heat the gas. Then suppose we consider piston comes here. Piston comes here. And suppose Vf is the final volume. That means there is expansion. Here we consider ideal gas. Ideal gas in a cylinder with movable, frictionless and massless piston. Vi is the initial volume. Now we heat the gas so that there is expansion and final volume is Vf. This expansion is isothermal expansion. That means we consider suppose 300 degrees centigrade. This temperature is same for both. Now we consider second case. Suppose we consider this is the first case in this and we consider the same is second case. Suppose here we consider this is the container. Suppose this is the container. Again here we consider same container. Now here suppose this container we consider, now this gas cylinder is surrounded by insulating material. Suppose I will show here. Suppose this is the insulating material. Here again insulating material. That means there is no exchange of heat. Insulating material. No exchange of heat of the cylinders with the surrounding. Suppose here we consider this cylinder divided into two compartments by a thin breakable partition. Suppose I consider here this is the partition, thin and breakable partition. Here we consider suppose V1 is the volume and here V1 dash is the volume. We consider suppose this cylinder is X, this cylinder is Y. Now here we consider suppose another cylinder here with having same volume. Now here suppose this is the initial state, and we consider this is the final state. 1 minute. Suppose this is the initial state and this is the final state. Now what we do here, suppose we consider that initial volume Vi, we consider it V1 plus V1 dash is equal to Vf. That means here you see this volume Vf and this volume Vf is same. Okay, that means this final state in first case is nothing but that is total volume Vf is equal to V1 plus V1 dash. Now compartment is empty. This compartment Y is empty. That means here is vacuum. We consider here vacuum in compartment Y. Okay. Now partition is suddenly broken. This causes a sudden uncontrolled expansion. Now the gas occupies this whole volume. This is Vf. Here no exchange of heat and also no work done because this insulating material is there. Therefore no exchange of heat. And this type of expansion is called as free expansion. Free expansion. For example, we will write puncture of tube. Here no change of temperature. Now in both experiments here, initial and final states are same. Here there are two different paths. Here we heat that is a cylinder. We give the heat from outside in case first. Now there is exchange of heat in this case, but here there is no exchange of heat. Therefore, it is concluded that heat transferred to a system, heat transferred to a system depends on a path. As in previous article we have studied, that is work done depends on path, and similarly here we have studied heat added during the thermodynamic process depends on the path. That means if we conclude for in this thermodynamic process, that is heat transferred, and suppose I will write here work done and heat transferred to a system depends on path of the system, path that system follows. I hope you all understand all about this thermodynamic process. Thank you.